So I'm going to front end this, and Larry, thanks for that kickoff. We call this, as you can see, Dante's Inferno. I think that will make sense as we move a little bit deeper into this. But what we thought we would cover here is a little bit of uncharted territory, if you will. There's been a lot of discussion around this level 0, level 1 of the Purdue model and the devices that reside there, and them being a little bit lonely and ignored in the security conversation. So we thought that we would bring some of that to the table today in addition to the cookies. So let me...
I think I might have to do that.
Oh, you're going to do that.
I'm going to do this. Right.
All right, so who we are not.
Yeah.
We are not the dog whisperer.
No, I've been confused with that guy. Like to the point where somebody took a picture of me and thought I was him. I'm like, I'm not him.
That's right. And
I don't think I look like him.
And then I am not Tim Medine. Tim is a much more famous, but a good-looking guy.
Yep.
At SANS. So if you don't like the presentation, then we are those people.
Yes.
Okay. So to get us started here, let's think about, what do we do? Why do we make stuff and move stuff and all of that? And where are our objectives in running these systems? If you're a plant manager, you want to have oversight as to the operational characteristics. How productive is my system? Am I running at peak efficiency? If you're an operator, then your view is a little bit different. Because you may not have that broad perspective. You might just be looking at a particular small aspect of the machine. Or if you're the maintenance service support person, then your view, of course, may be even different, even deeper into the actual logic, the configurations, et cetera. So having views of what's in these systems really varies by the roles and the responsibilities of the individual. Our prime objective is to, of course, run this safely and securely. But the data that provides these views really emanates from the same core elements within these systems. It's the I/O side of things, hence how we've themed this presentation. So Jeff, if you could go to the next one. All right, just some basics.
Sorry.
Maybe back one.
If
you can't, we could stick with this one too. Yeah, you could just leave it right here.
All right.
All right, so just some of the basics around control. Yes, we have an input. We process something, we make a decision based on that input, and we generate an output. And generally in control systems, that output is ultimately going to become some type of a physical output, hence the word cyber physical that continues to gain popularity. And we are surrounded by so many different intelligent devices, and of course more every day. The Internet of Things is definitely a core part of how we talk about these devices and these systems. And if we just reflect a moment on how many different control system application types there are, I'm assuming that on that right-hand side, one or many of those systems are something that you can relate to. Either you were a part of engineering and architecting or installing, or definitely have exposure to these types of systems, whether building automation. If you're driving a smart car, you just experience that every time you jump in a vehicle, shipping, oil and gas, et cetera, et cetera. So intelligent devices, the data that is created from these intelligent devices, these devices deep in the architecture are what is driving these systems. So go ahead and proceed. We showed this picture a little bit earlier today, and what we see here from a concern level is that devices and things are of grave concern to those of us responsible for these systems. We hear a lot about how important it is to know what's connected. You can't protect what you don't know is connected. And the previous panel we had, you can't have a safe system unless you know what's connected. So those devices and things are extremely important for us to have a handle on how many are connected and the type of data that is being supplied, and the trust that we put in those devices is pretty clear, I think. So Jeff, next one. And if we look at evolving risks to the industry, The history of different incidents and different attacks on companies and different campaigns, in almost every single case, the motive has led to an objective of reaching the endpoint and affecting an endpoint, affecting data to affect the operation. We're not going to dig into the specifics on any one of these, but data is the driver. That is the nature of the control system. That's how it's been engineered. So Jeff, next. So we have called this demo Dante's Inferno because the Purdue model that you see on the right-hand side there, I mean, this is a 30-year-old plus model that really gives us an architecture for building a system that the processes are segmented in that system. It gives us the ability to control the operation of that system and also have an understanding of the data exchange between different levels in this model. But it was never developed as a security architecture. It's been repurposed as a helpful way of thinking of how we can bring security into an architecture, but fundamentally it wasn't developed that way. And the Dante's Inferno,
Sorry.
no, that's okay.
Keep touching stuff.
That analogy is just to remind us that given all of these levels, right at the bottom there, that bottommost level is an area that can either help us or dramatically hurt us if we lose trust in the data that's provided from those most simple of devices. Jeff, next one. And the trustworthiness of those types of devices, analog and discrete devices, you know, your 4 to 20, 0 to 10, your discrete I/O, but then also some technologies that are extremely well established, like HART technology reaching instrumentation, and that will take the center stage in Jeff's demonstration, is the ability to not only pull I/O information, but the ability to use those same channels to configure and collect and calibrate those devices. So Jeff, next one. You can just hit it one more time. And I'll finish on this and then turn it over to Jeff. The reason why we undertook this is really to serve you cookies today, but to also make sure that we're not losing sight of what actually is within these systems. It's more than just the PLC. It's more than just the HMI. There are many I/O devices that will outlive the controllers. The field wiring in those I/O devices can stay put as systems evolve. So with that, I'm going to turn it over to Jeff. Jeff's going to take it from here, and he's going to start telling us a story about the importance of these devices. And I'll serve cookies if they're done, I guess.
Yeah, these ones are probably done. So how many folks are familiar with the Purdue model? So lots of people. Yeah, awesome. So it's an abstraction of the factory from an automation perspective, right? And lower levels end up being the genesis of the data. They send them to higher levels, and then we keep working on the data. We either store them or do whatever. What's a little bit interesting is there's a lot of focus and a lot of courseware and a lot of things that you can just get readily about the information and how you secure computer resources. And a lot of times we don't think about where the data is coming from. It's getting transacted to some kind of database, and we trust that it's good. And what we're actually just reminding ourselves of today is that inside the PLC, a lot of times is where the part count, the OEE data comes from, all that kind of stuff. And whether we like it or not, a PLC is just programmed to respond the way the program is, and we're going to run through that today. But whether or not it's good or bad information, whether an instrument is calibrated or not, it is what it is. It's just performing actions based on a set of control rules, right? So real quick question, how many folks here actually program PLCs for a living or process automation controllers? So we probably have 20%, I'm guessing. How many folks are consuming data from PLCs? Like database-y kind of things, or historians, or whatever. So a lot. So it's kind of that upside down wedding cake. So a lot less people that we interact with, especially in these kind of forums, are actually the folks who are in their seats actually programming PLCs, which is interesting. So let's go through how a PLC actually works. I've done this talk and discussion before, and I've had folks come up and say, I never really knew how a PLC really does work. So this is kind of a simplified version of how a PLC works. There's kind of 3 or 4 major components to a programmable controller of any sort, be it language types or whatever. At the top, there's this code execution engine. So we're really familiar with that. We write ladder code, we write instruction, we write function blocks or whatever, and at the end of the day, it gets compiled down to these embedded devices that we call programmable controllers. And it just runs through a lot of it is, if this and this and this or that and this, then turn an output on, right? So the compilers are quite extravagant, so the visual tools that we work on, but when you actually compile it to some specific ASIC, a lot of the vendors have their own specific ASIC to run these algorithms very quickly. That is kind of our front end to it. I'm going to skip down to the bottom. There's an input and output image table normally. That's the old school name for it, but it's basically, we read inputs like our body reads sensors, just like our nervous system, right? And the PLC is the part of the brain. So we're going to read inputs like how hot is it, is a particular switch flipped. So we're going to look at that, and we're going to write our if-then-else rules to that. And then there's non-I/O communication. So there's HMI stations where folks are interacting with the PLC. They're saying, hey, I want you to start this mode, or I want you to fill this tank. So those are the kind of communications that also come in. And then right in the center is kind of the jewels of a PLC. It's where the data table lives. So what happens is, when we actually walk through how this works, we'll read the input. So we'll read the sensors, whether they're on or off. We'll then update the data table or the image table. So we'll say, hey, this thing went from a 0 to a 1, so we can look at a current copy of the state of all of our inputs and outputs. We look at the logic and we solve it. So in this particular instance, if we had a permit action input, whether it's a push button or a limit switch or something like that, it would turn that output on. The data table gets updated, and then we actually push that new status out, which is actually now an action. So that goes from, like Doug likes to call it, cyber to physical. So we move from logically solving that, let's turn the output on. So for me, a lot of people will think that the ladder code or whatever is king. So if I understand that ladder code, I can actually understand how a process works, and that is very important. But if I can just go dance through the data table, I can actually, kind of skip the whole logical solving, and I can actually just affect the outputs right on the image table, or on the physical, solenoid valves or whatever. So I want you to kind of think of that a little bit. So for instance, when we're baking cookies here, how many folks are kind of aware of closed loop control, like PID control? So, wow, you guys are awesome. So most of you understand it, and it's basically, I'm going to say, if I have a particular input, like my actual temperature is 31.5 degrees C, and I'm trying to control to 26, well, my actual temperature is over, so I'm going to leave my output off. I'm going to let that thing cool, right? But if, like Skeletor or myself or the Dog Whisperer or somebody actually got in there and manipulated, let's say, scaling values, or I was able to say, hey, let's manipulate a scaling value to where it actually thinks it's lower temperature, then my program is set to say, hey, let's turn that output off and let's make the heater elements come on, or whatever, my infrared heating element, whatever. So what's a little bit sneaky about this is that I haven't changed the logic. I haven't changed the way this thing operates. So it's kind of a stealthy way to kind of sneak in or accidentally do something to your process, right? So just by having a sensor that doesn't really quite read correctly, or if I get into the data table and I override the sensor values, then I can affect how this works. Again, there's no alarms to this situation or this scenario, so it isn't really that, hey, somebody changed the code and I notice it. It just looks like normal operation. There's no alarms. There's nothing happening. There are ways to protect against that. We can talk about that later, but just generally understand that the joules are basically the data table. If I can get in and manipulate. Again, you could change the program, but it gets a little noisy if you're actually trying to do something on the nefarious side, or if I've brought a calibrator out or done something and I've changed the values while Doug talks about it as trying to change the wheels while the car's in motion. So while a process is running, I'm calibrating something, and whammo, the output changes, or the values change, therefore the output's going to change. So it's not only just I/O that's going to talk to it, but on the right-hand side you can see where in the non-I/O systems, like the HMI or like peer-to-peer controllers, I can send a message to another controller and I can say, hey, here you have a permissive to do something, and away it goes. I can use a programming terminal, which are what most folks think of. They say, if I can just get to the programming terminal and use legitimate programming devices or programming software, then I can manipulate those values and data, which is absolutely true. Or I can do things which we're going to show you through OPC or other types of way to write to it, like historians and stuff. So if the PLC is kind of the castle for where we get the data, like get and set data, then we have to look at it, where are the holes in the castle walls? So again, on that right-hand side, I can do things through OPC writes. I can do things through historians maybe flooding it so it cannot talk to remote systems. I can do things where I do man-in-the-middle of HMI systems. Again, getting more advanced, but we're going to show some simple things here. Skeletor can do something where possibly he gets into the data table. You've transacted that up to a historian or some other data storage, and now you've transacted that piece of misinformation a lot of different places. So as we get a more connected world, I get questions about how possible is this? And it isn't staring us in the face, but it will be slapping us in the face at some point. As I deal with different customers and they have different services, maybe from like a Praxair or some other services, those folks are busy providing a product or a service to their customer, which is on site. And now all of a sudden, the end customer wants to know, I want to verify and validate that you have provided me this service. And so I see where those service providers are actually interconnecting into the end customer's infrastructure, and a lot of times it isn't really thought through. So in my prediction, I think there will be zones of trust where we actually look at service providers in their own kind of bubble or their own security, let's call it zone and conduit, and then you'll protect yourself from it. And I think that'll be a popular subject coming up. So again, plants want to consume that contracted data. So let's go into the demo. The demo architecture up here is pretty simple. I have a PLC up here, and I don't have a pointer, but I have a PLC. I've got just an analog card here, a HART card here. Hooked to the analog input, I'm just running an analog input from a temperature sensor, but it can provide HART data, and I'm going to show you what you can do with the HART data there. Next to it, I have a HART card where I have this little puck, and I'm going to show you a picture here, but it's just a little, again, another temperature sensor, because I don't want to drag around more than just one oven. And the PLC is running its code. I've got the programming terminal set up, and so you'll get familiar with the architecture of what's actually in this box. This is not the right deck, so I will skip to where we want to go. So this is a picture of the hardware up here. And on the left-hand side is just a switch. So I'm communicating to Ethernet to the switch. It's connected to the PLC. These are the I/O cards. Here's a temperature sensor. Here's a temperature sensor. And I'm pulse width modulating this output that's hooked to the oven. So that's how I'm controlling the oven. I drilled a hole in the oven. One of the thermocouples is running into the oven. And that's actually what I'm doing. So what I want to do is skip here. And again, I opened up the wrong deck. I apologize. We want to do we want to do this one. So what we're going to end up doing is I'm going from the hardest to do, so like physical access kind of in your plant, to the easiest to do as we get out to OPC write. So with this system, I actually have a cable plugged into my programming terminal. I'm going to attach to that temperature sensor, and what I'm going to do is respan it, and then the PLC is just, again, operating on the sensor data. So all it wants to do is sit there and operate on it. So let's see here. If I go... Let's do this. So right here is the temperature that I'm reading from my second, in that first card. So I'm reading 76 degrees. So I'm hooked up to here, and again, there's two issues when you have smart instruments. You gotta calibrate the PLC information to what the sensor itself is doing. So that is, again, a little bit different challenge. But if I take and just change this to say 1500 or so, and I download, and this takes a little while, I'm going to actually see where my temperature starts to change. And again, it is, the PLC has no idea that this is actually going on. And if I were to use that in a loop, a PID loop, I'm not using that particular one on the oven right now. We'll mess with the oven here in a little bit. But again, this is moving from, this is a little bit harder to do because I got to have access to the front of that instrument. And then I'm going to move out to an actual HART network where HART networks can run, kilometers. How many have HART loops that they're using? How far is your distance, would you say? Like, is it little small or is it pretty big? Or say again? 1,200 feet. So it's not like I'm standing in front of it, but it is a possibility to move on to the instruments and calibrate. May I ask you how often you calibrate them? Fairly regular. May I ask why? Make sure they're accurate because it affects the process? Yeah. Did I have the same answer in the back, or pretty much? Correct. Yeah. So again, all of these things end up affecting. So now I've changed it to 71 degrees. So again, now if I look at my scaling in my PLC, I think it said 166 or something crazy right there. So now in that particular case, if my set point was 100, it would drive that output off, and I might be troubleshooting like, can't get this thing to go on, right? Or I've affected the process and basically turned it off. Let me do something else, and I'll go through this. So what I've done here, here's kind of the recap, is I've been able to affect the actual temperature, driving it up and down through the span. One of the other things that's kind of interesting is, so I've had people say, well, I don't give my E&IT techs or my instrumentation techs or anyone kind of that vendor software. So what I did was, out in the Wild Wild West, there's pieces of software that allows you to configure HART. So how many have used like Packware or some, yeah, so there are, like I just downloaded this, right? And so what happens is I am able to hook onto the HART network, which could be 1,000 feet or whatever. It could be anywhere. So I clamp onto that, and I can actually then reconfigure that instrument through HART commands. So this, although I'm just reading analog on that last one where it was scaled kind of weird, I can actually move from, let's say, degrees F to degrees C. So let's actually do that. So this is Packware right here. And what I'm going to do, and this may or may not CAC, is if I just move the temperature around from degrees F to degrees C, and I give it a write. So what I've done is I have moved that and written it from where the instrumentation piece of software has no idea that I've written to its own device. So if I go back here, let me turn this off. Yeah, so right there. So it's reading a 21.9 degree Fahrenheit. It has no idea because it was at, what, 60 something? So underneath its knowability, I've went in with a generic piece of software and rewritten to it, and its software is even messed up. So again, it's just knowing that how these systems work and how I'm able to actually affect the scale without instruments like this embedded piece even knowing that it got written to. All right. So I think the other one we wanted to do here was, say again, please. Yes, so in this particular case, like physical security is very important. And so that's why we're starting with the, I plugged into the front of it. That's hard to get a hold of probably in a lot of plants. But as I now start to expand to, thousands of feet of access, let's call it, anywhere I can clamp onto that network and reconfigure it. And it doesn't even have to be malicious. This gentleman's a great witness is that in my career and in yours is you end up calibrating this. This is not something that's just like, we never do this. This happens a lot. So knowing who's accessing this, knowing how they're doing it, and knowing that it's going to affect the process is really important. We can also do things with the tool where we're actually, for instance, let's say we're going to change the heart card. So now I'm going to skip over to where the heart card is. And there is a configuration here where it has a span on it, and it's actually run in this oven. I should probably turn it down because it might. Why don't I just do that first? So here's the PID, here's the set point. There's nothing in the oven, so I'll just do 200 here. So you'll see the output go to 0. What's also interesting here, let's see if I can do this. See if I can show you this here real quick. That's not like that. So when I talk about dancing through the data table, so if you can see that, you will here in a second, hopefully. All right, so that this first output, which will hopefully get in focus here in a second. So I talked about dancing through the data table. Let me do this real quick. So I have, you've seen me turn that off through the PID, right? The output went off, the output's not on. Oh, you're not? Yeah, here we go. Let me turn this on real quick. Boom. So I'm going to have this dance through the data table. This is where I was going to shuffle. You can watch Jeff dance. So if you look at this first one right here, that one right there, that first one, that's the heat output, and that there is pulsing that oven. So literally, if I can get to the data table, was my dance through the data table jiggle thing. So I just had it. I could manually do this, but I'm just sitting there pulsing the outputs. And that is the key to this message. If you go, oh my gosh, if I can get to that data table and turn things off and on, that's exactly what I'm doing. The PID thinks it's off, but right there it's on. So let me go back to this. So the other thing is that reconfiguring the heart card. Let's see here. If I go to 4. that one. I need to configure this one here. So I can reconfigure this. So this is setting, basically there's like, the way most of these cards work is I make all my changes and then I make a commit to the module and it makes a change. So for instance, if I change this to 1900, I might think in my smartness that it's actually committed it to the card, but it has not. There is it holds it. Let me find it here. Whoops. Move my hand right. Let's see. I called it. Right here. So once I figure out that how to make that PLC now transmit and commit that, I created this bit to make it do it. So now it's actually written that out there. So now my heart devices are being affected, basically. So, and again, that would manifest itself in a very different temperature range. So anybody got any questions? Because now I'm going to move further out. So that's kind of manipulating data tables through that. So, and again, I apologize. I messed up the order of the slides. Okay, here we go. Right here. Okay, so this is where you get my world's stupidest joke, but it is mine. So what's the two things that survived nuclear holocaust? Everybody gets the first one right. Cockroaches, thank you. What's the second? OPC servers, that's right, because they're everywhere like cockroaches. So that's my stupid joke. So, yeah, completely stupid. But they live everywhere. And the point to that is that there's this 3-move chess move that you can do with an OPC server, and you go, you're going to be an OPC server. So I go, hey, are you an OPC server? Yes, I'm an OPC server. Yes, I say, hey, OPC server, what tags do you have? So what's enumerated? So he tells me all the tags, and I find something interesting that's like, tank overflow or override, the world or something. And so I say, thank you. Then I manipulate that bit, and off it goes. And so the idea of showing you that if I can get a foothold in and I start enumerating where OPC servers are, because they are like cockroaches, they are everywhere, I will find one. I will absolutely find one in an environment. And it becomes like I'm not him. He's pretty awesome at manipulating things. I'm too lazy to be him. So I just go and find them, like, hey, are you an OPC server? And they say, yeah, sure I am. So I can manipulate that, and that's what we're going to do here. So first I take an OPC client, I do the enumeration, and I find what the tag lists are, and then I can start saying, I'd like that value to be this or that, and it writes it, okay? So, so I've got an OPC test client here, and I already created a connection to the analog card, and we can see that remember when we rescaled it and it's a really high number? So what I can do is I can rescale this again. So let's say I put this up to like 1500. So what I'm going to do is I'm going to synchronize a write. I'm going to do 1500. And then I go, aha! And like it doesn't really change. So then just like in my heart card, I'm like, oh, it's holding here. I need it to transact. So I figured out how to make that actually transact. So I'm going to dink that to a 1. And I should see a value change there, so it dropped a little bit. So what I could do is I could sit there and increment OPC from a very long way away. So we've gone from plugging in the front of something to manipulating all the way out to something that I'm going to find in an environment. So how do we kind of protect from that? So what we could do is we could, some vendors allow you to actually say these values are discoverable. These values are discoverable, but you can read them. These values are discoverable, and you can read and write them. So all I would do is I'm on a Rockwell piece of equipment, And what I could do is, in my monitoring of my tags, I could go over here and there's a field, excuse me, edit tags. And I can go over here and I can limit the read-write access. So what I could do for the values that I don't want to be written by OPC, I can set that to read-only so I can read them, but then I could also, that will eliminate this kind of tool or an OPC tool from actually writing and manipulating the data. Okay? Then last but not least is I wanted to show you, so the world is moving to a very connected place, right? And on this last, the round puck, it offers like a team collaboration, team configuration tools, all that kind of stuff. And so in this particular model, there's a near field that you can touch, which is, I'm too cheap to buy the expensive one. That's the one I bought. There's a Bluetooth version, and there's a wireless version, and a whole collaboration. So our world is moving to where the end sensors are actually becoming a team collaboration, because how many people work in a place where there are people who are responsible for instrumentation? And that's their jobs, right? So they want to participate in what's the health of my device. I need to continually configure it because it changes. It's also, I would argue, is because it's touching the process. I do some work in the poultry industries, and it's like everybody's walking on those things, and it's nasty, and they're washing it every day, and so those things die a lot. So they put them out there, they recalibrate them. So those things get touched a lot. So the last part of this demo is really just to make you aware that, that there are collaboration tools. And this one here is basically a tool, and yeah, you're actually seeing it, to where I can read a configuration. So I move it close to the transmitter, and it'll tell me what it's doing. I can say, hey, let's change that. Let's change this to, 1,000, something like that. I should be able to go down here and write it. So now I touch it, and I write it, and it's written it. And so I'm curious as to what it did to this PID value. Let's go back here. So it thinks it's 559 degrees now. So again, the PLCs are just acting on the data. So that is the last demo before we go to panel. Is there anything specific that you had questions about this? I have one recap slide. I think Mr. Wylie was actually going to wander up here and help me talk about it.
Hey Jeff, just from back here, stay on that slide for just a moment. So you have NFC, Bluetooth, and Wi-Fi. So
yes.
NFC is basically you have to have physical access to the device.
Correct.
Bluetooth, we know, is like 10 meters. However, there are amplifiers out there that can extend that distance greatly, and Wi-Fi, we know what the range is.
Yes.
So what I think I heard you say is that hockey puck, you could have had different versions that would have expanded accessibility beyond physical access.
Absolutely, yeah. So that's a great point. The demos kind of walked you from standing in front of the thing to thousands of feet to you're out somewhere and you've drilled in and you're either collaborating for the good or for the bad. So yeah, in this particular case, Wi-Fi enabled devices like Rockwell with analytics for devices. There's all these little pinholes that's going to come out into a cloud, and it's a way in as well. And it is on the device level. So again, I think we're going to see from where we can run things through one firewall to there's going to be all these little pinholes from Wi-Fi to cellular, and now we got to start thinking about it in those terms. Again, not here to scare you. I'm mostly here to just tell you how does a PLC work. It's just working on the data you give it, and it's just that simple. And then you can do, in my prediction is that just like there's software assurance for coding languages, I believe there will be two things. One is there will be security assurance for PLC, or from the PLC level. Did I code the thing right? Did I code the right thing? And then did I code the right thing? There will be, I'm going to call it languages because I don't know what else to call it, but like state transition diagrams. So it's the state model plus transition tables that'll tell you how did I verify this code that's in the PLC. Because right now, every vendor will tell you how to use their tool, but I've never seen where it's telling you how to actually solve the problem or the process control problem that you're trying to solve. They'll have templates and things like that, but it doesn't quite scratch the itch. So with that, oh yes, sir.
Yeah, I have a microphone, so if you have a question, let me just hand you the mic. And Jeff, we'll take questions specific to the demo for a few minutes, and then we'll switch to our panel discussion.
Perfect.
In the example that you used when you used the OPC client,
Yes.
if you had been using OPC UA, which has some inherent security features in there, would that have changed your ability to get at that PLC at all? Or
No. So the question is, does OPC UA help you with that? And I'm saying no, and here's why. Every OPC stack, let's see if I can show this on one of these here. So my joke, it's not a joke, but it is, I've had a lot of conversations about people talking about OPC, and they say, well, I've got OPC, so it's secure, whatever. But the only thing that this processor talks is SIP. So it's this Control and Information Protocol, or they changed it to Common Information Protocol. A PLC5 talks, PC cubed. Siemens might be Profibus, Profinet. So at some point there's a stack inside of these drivers that converts it from OPC to SIP on the wire. And because this is an open protocol, and this thing only knows how to talk SIP, and it knows how to say, like, hey, I need a forward open, get attributes all, what's the class incident attributes, blah, 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 and so all of a sudden I've got this picture of what's running in there. So the answer, my short answer is no. That was my longer answer of why. Anybody else?
No other questions about the demo?
Anybody want cookies? We got some more. We got about 9 up here, 9, 10, 11, 12.
Oh, we got one more question here. Can you hand that
The record is 120 with a size about like you guys, so you guys are underachieving on the cookie intake so far.
So your solution for the OPC vector, so to speak, would be to use the read-write access in the controller, switch that to a read-only tag, for example.
Yeah.
What do you do in the situation when you're needing that to be read-write for the use of your SCADA system? That's how you write your set point from your SCADA system.
So the question is, if I flip that to read only, then I've locked myself out probably from other tools. My guess is that your SCADA system isn't going to be talking OPC to it. So that's one thing, right? So you could have where it's just transacting. This is a read only for OPC, and this is read write for comms that are native. That's one strategy. Obviously, locking down the infrastructure. So things that are talking OPC out the top, I prefer that they don't write, but that's just me. So, because a lot of times, so the OSI, anybody from OSI Pi here? If I say something bad about OSI Pi, nobody's going to punch me. So if you look at their models, and they say, okay, here's, and this gentleman wrote a heck of a paper on the OSI, using it as a intrusion detection some years ago. But with their chief security person, when you want to pull from Pi, they can really secure that very well. So it's like I'm transacting data up and down, or up. I'm just pulling it out. That's pretty securable. When you want to do read and write, they kind of punt, because that's a pretty hard situation to know what's in scope and what's not. And so that's kind of why I fall back on this easy answer of, I like to know who's writing the data and make sure that's something I can secure. But like historians and different things from out across the fruited plains kind of scare me. Again, it's a risk versus reward. Like this whole week will be, there are some customers, like literally I've been in the Little Green Army Man factory, and like ladies pulling out bazooka guy and this and that. And I'm like, why don't you just have the mold do this? And then, but they don't care. It's like, I don't care. But I was also in the place where they make open heart valve pieces. They care. They cared a whole lot. So it's a whole weighting scale of what your customer needs and what are you willing to assume as risk if I let an OPC server write. So, anything else? Yes?
So we understand the risks over here with with the data table being exposed. Aren't the vendors, Siemens and the Rockwells, aren't they doing anything about this? I mean, this is a standard fix over here would be encryption and device-to-device encryption or a communication encryption. Won't that address this kind of issues?
Actually, if I could recommend you save that question for the panel, because we have two other people that can address that question as well.
Okay.
That's a great question for the panel. But Jeff, if you wanted to say something.
Yeah, my quick answer is encryption isn't always the answer for everything, but knowing who's talking to it and then protecting the rights and privileges of who can use that box to talk to it is real important, hugely important. But again, if the panel members want to weigh in, that would be awesome.